Hello everyone and good afternoon. Today I'm going to present our paper entitled Days of Future Past, an optimization-based adaptive bitrate algorithm over HTTP3. I worked on this paper or this project with my colleagues from the University of Klagenfurt. I would like to start with the agenda, so a bit of introduction on the topics that will be touched throughout or covered throughout this presentation, the motivation that led us to the development of this approach, an in-depth of this approach and proposed method, the experimental setup and the conditions of the system, results, analysis, and comparison between the state-of-the-art approaches, and conclusion and final remarks. For the introduction, I would like to start with the HAS schema, so the HTTP adaptive streaming schema. We start here on the left corner with the video reproduction and the video segmentation, which means that we are splitting the video reproduction, the video file in different segments. After this segmentation, there's the video encoding, which means that starting from the high resolution video, we want to create different versions of the same video. And different versions are, each version is characterized by a resolution and a bitrate. After these versions, the different versions are created, the client, which can be a smartphone, a tablet, a laptop, can request these segments via HTTP GET requests, and the server will then answer by sending these segments to the client. And these segments, why or which segment do we need to download? How can we decide which segment? Well, the decision is done could be done on the throughput of the system, so the network condition over time, or on the buffer estimation or the buffer level, which is the amount of segments that are actually stored at the client side. And this decision needs to be done by the adaptive bitrate algorithm, ABR algorithm. After these segments are downloaded, there's the video decoding, and then the segments are displayed actually on the client side, on the client screen. The second topic, really important, is HTTP3 and quick. We decided to run our application on top of HTTP3 and quick because we wanted to exploit it. We wanted to exploit the features of HTTP3 and quick. And the first feature that I'd like to talk about is a zero RTT connection establishment, which means that the data are exchanged immediately after the connection is established. That's why it's called a zero RTT. Then the second important feature is called stream multiplexing, which allows us to create different independent and concurrent streams at the same time. And the independency of the stream is also enhanced by the fact that Quick runs on top of UDP, which means that each stream suffers less from head-of-line blocking. The third important feature is the stream termination, which means that we can cancel one stream or many streams if they carry some data that are no longer of interest for us. Then the motivation. Why did we decide to pursue this approach? This is a figure that depicts the situation of buffer, of the client buffer at a specific time t, at a general time t. We can see here from I-3 to I are the indexes of the segments stored in the buffer, and I+1 is the next segment. The state-of-the-art approaches only focus on this one, only focus on the next segment, I+1. So why, if we have some segments, as we can see here, I-1 and I-2, whose qualities are not good enough, and if we had enough throughput to also re-download this at a maximum quality, why shouldn't we do it? This would enhance the QE, the quality of experience of the user, as it's enhancing the average quality, increasing the average quality. Now the proposed method. So the mixed integer linear programming model, or DOFP, selects the bitrate for the next segment, but also which segments from the buffer need to be upgraded and the bitrate for this segment. So how much are we upgrading these segments? Here there's a table with the parameters that are used in the next slides for the constraints that we applied to the model. I would like to briefly introduce them. Um, B is the set of the indexes of k buffered segments plus the next one. So with the next segment, in total is k plus 1 indexes. Qi is the quality level of the segment index I. Aij is the binary variable stating if one, whether the re-download of the ith segment at quality j is needed. Di is the deadline, the playout deadline to re-download for re-downloading the segment index I. P now is the current buffer level. P max is the maximum buffer size, the maximum amount of segments that we can store at the client side. Sij is the size of the segment I, which is quality level j in kilobits. Ti is the assigned throughput for re-downloading the segment I and will be selected by the model. And omega is the available throughput between the player or the client and the server. So let's start with the first constraint. The first constraint expresses the univocity of the pair index quality, which means, as we can see here from this expression, only one quality can be selected for each segment. So for each segment here in the set B, we want that the sum of the binary variables is one, exactly one, which means only one quality for each segment. As we can see here, J goes from 1 to L, where L is the maximum quality level. For the second constraint, we need firstly to define the deadlines for each segment, where alpha, beta, and gamma are 3 parameters, and mu is the so-called safety parameter or safety margin. And what is the deadline? Deadline is, in the case of the buffered segment, the playout deadline. So the amount of time that that separates the beginning of the buffer from the actual time that the segment in the buffer will be played out. So the deadline expresses the time that we have available, the available time for re-downloading a specific segment. And for the next segment, we define different ranges, um, different values with respect to the zone that the buffer level is within. So if the buffer level is in a dangerous zone here, we can see the first zone, the deadline for the next segment will be the segment length times a sort of weight, which could be 0.9 as the safety parameter, could be 0.1, for example. And as we go further towards the maximum buffer size, we can see in the middle zone, so middle dangerous zone, the deadline for the next segment will be the current buffer level minus the lower threshold of the dangerous zone. And with the same purpose, with the same goal, we define for the last area, for the last region, the deadline as the current buffer level minus the lower threshold for the middle zone here, we can see. And now we can define the second constraint as we can see here, which ensure that the download time is lower than the deadline, which means that the download of the segment I, here we can see the download of the segment I, which is expressed by the size of the segment I with quality J, and here the throughput assigned to re-download this segment. So the size divided over the throughput is, if we take the throughput on the other side, is the download time, which needs, as we can see here, to be lower or equal than the deadline. And this condition needs to hold not for all the J, not for all the representation, but only if the quality selected by the model is greater than the previous one. So if the quality selected by the model is equal to the buffered quality, we don't need to re-download anything. So this condition doesn't need to hold, mustn't hold. The third constraint checks that the sum of the assigned throughputs, so the assigned throughput to each segment, is at most equal to the available throughput, the available one. And we can see here if there's no multiplexing, so in normal condition, the sum of the throughput assigned to each segment needs to be lower or equal than the available one. This is another condition with the multiplexing because the multiplexing feature in HTTP3 and QUIC is really strict and doesn't allow us to split bandwidth, let's say, as we desire, but it splits the bandwidth equally, which means that for every Ti, we need to set this condition to be Ti lower or equal than the total available throughput divided equally through the k plus 1, so the buffered segments and the next segment. Lastly, the MLP model is introduced as follows. We want to maximize the J star, which is the minimum quality among the segments. As you can see here, J star needs to be lower or equal than every other J, every other quality in the set B. Plus, also we want to introduce another factor, which is the quality for each segment, which is the sum for all the segments of the quality value. This model to this model needs to be applied these constraints that I said that I explained in the previous slide. So from 1 to 3, and the variables considered are the aij, so the binary variables, which states whether the segment I needs to be downloaded at quality J, and the throughput assigned to each segment. The experimental setup, we used an HTTP adaptive streaming testbed with the LS Quick platform, which is a platform that allow us to build an application on top of it and exploiting its implementation of the HTTP free and quick. We also use 5 minutes the sequence of Tears of Steel, the beginning part, and this bitrate ladder, as you can see the reference here, with 7 different levels and the resolution, the respective resolutions here. The codec is H.264. We use the traffic control bash script to manage the throughput to simulate a 4G network trace with RTT 40 milliseconds. The segment length is 4 seconds and the maximum buffer size is 20 seconds. These are the parameters for the deadline computation of the next segment. So results and analysis, we consider different metrics. The average quality, which is the average quality level of the played segments, the segments played out. The video instability, which is the average quality fluctuation among adjacent segments. The number of switches, which is the number of segments whose quality is lower than the previous one. The stalls, the number of buffer underruns. The stall duration, which is the total time that the video freezes. And lastly, the QE score, which is a score computed by ITUT P1203 with the mode 0, and we utilized its extension, whose reference is here. We used and developed this for different approaches, different versions of the DFP. The B version is the basic one. The next segment is firstly requested and downloaded, and then the retransmitted one sequentially as they appear in the buffer. Then we have the M, which is the stream multiplexing feature. So the DFP with stream multiplexing feature and concurrent requests. The C with stream cancellation. And the MC, which stands for both. So multiplexing and stream cancellation. In this table here, we can see the different results and the best results in different colors. We can state from this table that the best results are achieved when the multiplexing and cancellation features are utilized. We can see here multiplexing feature, best results, and multiplexing plus cancellation features, best results. We can state then that the multiplexing and cancellation feature enhance the DFP results. So for the comparison of the state-of-the-art approaches, you can see here we have different state-of-the-art approaches. The first one is the AGG, which is the throughput-based AVR algorithm, which aggressively tries to enhance the quality of the downloaded segments. It will select the bitrate of the segment or the segment whose bitrate is the maximum one, but lower than the throughput, the available throughput. The second one is BOLA, which is a buffer-based approach, and it exploits the Lyapunov optimization, and it tries to jointly maximize two utility functions. Then we have Sarah, which is a hybrid approach, so both based on throughput and on buffer, and it used similar zones or similar ranges as we defined in the deadlines, where it can decide to increase more or less um, hard the bitrate or the segments. And lastly, we have BBA0, which is a buffer-based ABR algorithm, which used the linearly incremental function to linearly incremental function of the buffer to decide which segment, which quality should be downloaded. So we can see here Sarah and DFPMC, the comparison. Sarah provides the highest percentage of quality 7 segment. As we can see here, we have the played out segments based on their qualities for each approach. 74%, and the average quality is 6.12, whereas DFPMC provides a good result with 64% for the highest percentage of quality 7 segments and 6.02 for average quality. But DFPMC provides the best result for the lowest percentage of quality 1 segment, which is 3.2%, whereas the others perform badly, let's say performs worse, with 6.1% minimum or over 6.1% for the lowest percentage of quality 1 segment. The second metric, as I said, is the number of switches and video instability. BBA provides the lowest video instability with 0.53. Whereas DFPMC provides the second lowest with 0.54. DFPMC also has the high, not the highest, but a really high number of switches, 10.6, where we can see the other has not so high number of switches. But the point here is that DFPMC does not try to eliminate the gaps, but rather to upgrade the quality, which means that we can have high number of switches, but if we have a low amount of video instability, it means that the switches are not so high value. Then the comparison with the state-of-the-art approaches, we can see for the number of stalls and stall duration, DFPMC outperforms the other with 0 stalls and 0 seconds of stall duration. Whereas AGG, for example, provides 0.4 and average stalls and 1.47 seconds of stall duration. And the worst result is performed by BBA, scored by BBA with 4 stalls and 14.41 seconds on average. Lastly, for the QoE score, DFPMC also scores the best QoE value with 3.38. with up to 33.9% increment with reference to the other approaches. We can see here the trend of the QoE score. For the conclusions, DFPMC is a MIRP model which provides a high QoE score and a low stall probability through HTTP-free and quick features. Taking into account the throughput buffer and also the quality of each buffered segment, the model chooses the bitrate not only for the next segment, but also for the buffer segments to be retransmitted. The FPMC also outperforms the other approaches with the highest QoE score, and multiplexing feature and cancellation feature enhance the DFP results, as we saw in the table. In the future, we plan to investigate the stream priority feature, the impact of DSP parameters, for example, alpha, beta, gamma, and mu, or different streaming scenarios for video sequence, bitrate ladder, segment duration, and so on. And also for the network scenarios, we plan to use different bandwidth traces. Thank you for your attention, and please feel free to ask questions.
All right, thank you very much for the presentation. I just realized that I forgot to introduce you. My apologies. So this is again a paper from a group that we've seen several times in the past when it comes to media and video streaming over QUIC. They've done some very, very interesting work. And again, it's nice to see some new faces there that I previously hadn't heard of, like the first author of this paper, who just presented. Again, hoping that that will bring more new researchers into this field as well. Is there anyone who has a question about this paper presentation in the chat? Please let us know. Guillaume asks, how does the access link quality of the client vary over time? And are clients homogeneous, or are there groups of clients that you are simulating at the same time? So Danielle, I think you're muted.
Yeah,
that's perfect. Hello.
Yeah. Are clients homogeneous or are there groups of clients? Actually, we used one client. We used, as I presented in the presentation, virtual machine, like 2 virtual machines, 1 client and 1 server on a host, and we use that to test the performances on the quick and on the metrics that I explained.
So how do you vary the link quality? So you mentioned the 4G trace. What exactly does that mean?
Yeah, we actually, as you can see in the chat, there's also the other co-author, Min, who answered the question. We used a traffic control script, a bash script, to simulate a 4G trace, and that followed basically a real trace, a real trend for video streaming. We use that as a real trace, real simulation.
Yeah, but what do you simulate? Only throughput, or also variable RTT, also packet loss?
At the moment, we only used as RTT 40 milliseconds and only 1 sequence, but we plan in the extension on the journal version to also update and introduce, as I said in the final remarks, also other scenarios to enhance also the results, the evaluation.
Okay. Anyone else? Okay. You seem to have answered the question. Anyone else a question? Please let us know in chat. I myself was a little bit confused about how exactly, or let's say why you need multiplexing. The way I understand it, if you have the different segments of the video, you always want to be playing the latest one, right? And they will always be played sequentially. So you wouldn't really want to multiplex multiple segments at the same time, because you will be sending data for things that will be paid much later together with things you need right now. So why would you ever want to do multiplexing instead of just sequentially sending the segments? I don't really understand that.
Because the investigation needs to be done like really in deep, and that's why I also plan to do it in the next steps. But we wanted to let's say to test and to evaluate also the results by sending not only the request sequentially, but also sends the packet from the server to the client, like concurrently with multiplexing, to see so we didn't only try to send the requests sequentially and with multiplexing, but also try to update and request the packet from the server with the basic version sequentially and with the multiplexing, just to try to measure if with the multiplexing we had some kind of improvement. And in the table,
I get that, and you show improvement, but I don't understand why. I'm wondering if you understand why.
Yeah,
because you're delaying important data right now for data that you will need later, if I understand.
Yes. We need the data as soon as we are playing out the segments. or I mean, we want to receive these segments, of course, before, as I mentioned, the deadlines for the playing out of the segments. And the way I see the multiplexing feature is helping us because when we are requesting some segments and when we are delivering these segments, we don't need to wait for the segments like sequentially to be received, but we can send every segment like at the same time by splitting the bandwidth in this case, and we can show some improvement in doing that. That is the purpose of our work.
Yeah, I don't want to keep on going on this. I just don't understand. You have a critical segment that you need first, but you lower its bandwidth so that you can also send the segment you need later. And so it would make more sense to me to have full bandwidth available for the first segment and then have full bandwidth available later for the later segment. But I'm sure I probably am missing something there. It's definitely interesting for me because that's the level that I mostly work on to see this type of results. This means I'm probably still missing something there. So useful results, I think, from you guys.
I think if Min wants to add something, I would be interested.
Yeah, Min, do you want to comment on that?
Sorry. I missed the questions about that.
I'm wondering why do you think multiplexing helps? Because to me that's counterintuitive. Because you are wasting throughput, you're wasting bandwidth on things you need later, and you don't have the bandwidth available for things you need right now.
Yeah, in some cases, that's right. But actually, like as you can see in the results, the main idea is like if we don't use multiplexing and in case the RTT is high, so if we just send the segments one by one, so we received one segment and then we need to request one more time, so we have to wait one RTT. So that's in that time we don't use. I mean, like the client cannot download any new data. So that means we don't use the throughput efficiently. And also then, but when we use multiplexing, okay, we can have a risk about like we cannot have enough like much throughput for the later or for the later segments, but because in our optimization model we also take it into account we also take into account the available throughput of for each segments, and it can help us like download it more efficiently when we share the throughput. And also we have us to use cancellations, because if we do, yes, that's right. Yeah,
the cancellations, I fully understand why that's useful. It's just but so I suggest we take this as we say in the ITF off list. It's definitely interesting. I love to see this kind of results that is a bit counterintuitive. That means we can do some follow-up work.
Actually, it's just like initial results for us, and we really need to take dive more details about also the implementation. Maybe it can have some problems about that, and yeah, we can open the work in the later work.
Exactly, that's what I mean. That in the introduction, the work has only started, right? We're still figuring things out.
Yeah, kind of that.